Far beyond Mars, beyond Jupiter and Saturn, and even beyond the familiar icy moons that dominate most discussions about extraterrestrial life, there exists a group of worlds that almost never make headlines. They are distant, frozen, and dimly lit by the sun. And yet, they may be some of the most scientifically fascinating places in the entire solar system. Among them is Triton, the largest moon of Neptune, and several mysterious moons orbiting Uranus. These worlds should be geologically dead, but the evidence suggests otherwise. Triton immediately stands out as an anomaly. Unlike almost every large moon in the solar system, Triton orbits its planet in the opposite direction of Neptune's rotation. This retrograde orbit strongly suggests that Triton did not form around Neptune at all. Instead, it was likely captured billions of years ago, possibly originating in the Kuiper Belt, the same distant region that produced Pluto. This single fact already makes Triton unusual, but what scientists discovered next transformed it from a curiosity into a scientific paradox. When Voyager 2 flew past Triton in 1989, it revealed a surface unlike anything expected at such extreme distances from the Sun. Triton's surface temperature averages around -235 degrees Celsius, making it one of the coldest known surfaces in the solar system. At those temperatures, geological activity should be impossible. Ice should be rock-hard, chemistry should be frozen in time, and the moon should be inert. Instead, Voyager 2 detected something extraordinary: active geysers. These geysers were not driven by water like those on Earth. They were composed primarily of nitrogen, erupting from beneath Triton's icy crust and blasting dark plumes kilometers into the thin atmosphere. The presence of these geysers meant that Triton was not dead at all. It was active, and geological activity implies one thing above all else: internal energy. Scientists believe this energy comes from a combination of tidal heating and residual heat trapped beneath Triton's thick ice shell. As Triton orbits Neptune, gravitational forces subtly flex its interior. Over time, this flexing generates heat, much like bending a paperclip repeatedly causes it to warm. Even a small amount of heat, when trapped under kilometers of ice, can be enough to maintain a subsurface ocean in a liquid state. This idea places Triton in the same category as Europa and Enceladus, moons already famous for their hidden oceans. But Triton may be even more intriguing. Because it likely originated in the Kuiper Belt, its composition could include complex organic compounds preserved from the earliest days of the solar system. In other words, Triton could be a frozen archive of primordial chemistry, potentially mixed with liquid water beneath its surface. Liquid water, energy, and chemical complexity form the foundation of what scientists consider the basic requirements for life. Sunlight is not strictly necessary. On Earth, entire ecosystems thrive in the deep ocean around hydrothermal vents, completely isolated from the sun. If similar environments exist beneath Triton's ice, then life at least in microbial form cannot be ruled out. But Triton is only part of the story. Even farther from public attention lies Uranus and its system of moons. Uranus itself is strange, rotating on its side with an axial tilt of about 98 degrees. This extreme orientation creates unusual gravitational and thermal conditions for its moons. For decades, these moons were considered frozen, inactive, and uninteresting. Recent research suggests that assumption may be wrong. Moons, such as Miranda, Ariel, and Umbriel show surface features that hint at internal activity. Miranda, in particular, displays chaotic terrain, enormous cliffs, and fractured regions that appear to have been reshaped from within. These structures are difficult to explain without some form of internal heating. Reanalysis of Voyager 2 data, combined with modern thermal and orbital models, suggests that some of Uranus' moons may also harbor subsurface oceans. These oceans would not be warm. They would be dark, cold, and buried beneath thick ice shells. But they may be salty, and salt lowers the freezing point of water. Salty oceans are more resistant to freezing completely, especially when even small amounts of internal heat are present. Additionally, salty water is electrically conductive, which means future spacecraft could potentially detect these oceans indirectly by studying magnetic field interactions. The existence of subsurface oceans around Uranus would dramatically expand the number of potentially habitable environments in the solar system. It would also challenge the long-held assumption that only moons orbiting giant planets like Jupiter and Saturn can maintain internal oceans. Uranus, despite its distance and low heat output, may host multiple ocean worlds quietly hidden beneath ice. This leads to a question that extends beyond astrobiology and into the future of humanity itself. Could these moons ever be considered for human exploration or even colonization? Colonization, in this context, does not mean building cities on the surface. The surfaces of Triton and Uranus moons are far too cold, irradiated, and unstable for traditional settlements. Instead, any long-term human presence would likely take place beneath the ice. Subsurface habitats could be carved into or embedded within the ice shell, using the ice itself as a shield against radiation and micrometeoroids. This idea is not as far-fetched as it sounds. Ice is an excellent radiation barrier. A few meters of ice can provide more protection than thick layers of rock or artificial shielding. Beneath the surface, temperatures would be far more stable than on the exterior, reducing thermal stress on equipment and habitats. Water ice could be melted and purified for drinking, oxygen production, and fuel generation. Triton, in particular, offers an interesting advantage: nitrogen. Nitrogen is abundant on Triton's surface and in its atmosphere. On Earth, nitrogen is essential for creating breathable air mixtures and for supporting agriculture. A future outpost could potentially harvest nitrogen locally rather than transporting it from Earth, dramatically reducing mission costs. Energy would remain the biggest challenge. Solar power is weak at such distances, but nuclear fission reactors or even future fusion systems could provide stable, long-term power. With sufficient energy, heating subsurface habitats and maintaining life support systems becomes feasible, at least in theory. Even if permanent human settlement never becomes practical, robotic and temporary human missions to these moons would still be revolutionary. Studying subsurface oceans directly would provide unprecedented insight into how common habitable environments are in the universe. If life were discovered beneath the ice of Triton or a moon of Uranus, it would mean that life can arise in conditions far more diverse than previously believed. Such a discovery would reshape our understanding of biology, chemistry, and the uniqueness of Earth. It would suggest that life is not a rare cosmic accident but a natural consequence of the right physical and chemical conditions. And those conditions may exist on countless icy worlds scattered throughout the galaxy. Triton and Uranus moons remind us of something important. The most profound discoveries are not always found where we expect them. While Mars continues to dominate public imagination, these distant frozen worlds quietly challenge our assumptions about habitability, life, and the future of exploration. They are not dead worlds, they are hidden worlds. And as technology advances, they may one day move from the margins of scientific interest to the center of humanity's greatest questions. If we overlook Triton and Uranus moons for so long, one can only wonder what other worlds we have yet to truly see.